All right. So we have our next speakers. They are core developers. I don't need to introduce them, but we have Keno, who has always pushed the boundaries in terms of what the Julia can do, and Shuhei has been working on all of these static analysis libraries like JET, and they'll present more on the internals of static analysis in Julia. So you can.
Perfect, thank you. Very happy to be here for my 11th JuliaCon. First time I'm playing a stadium, though. So that's definitely going on the resume. I'm here with my colleague Shuhei, and we're going to be telling you a little bit about some of the cool new features that we've been adding to the compiler over the past, let's call it 2-3 years. Before I do that, though, I want to give you a little bit of a conceptual framework for what it is the compiler is doing. And the place I want to start is the method table. So if you've attended any sort of introductory Julia talk, one of the things that the presenters will often do is show you an exit of the method table. For example, in this case, the method table where all the first arguments are equal to plus, and then tell you something like, this is sorted in my apologies. This is sorted in specificity order. And the thing that Julia does is, at every call, control transfers to the most specific applicable method. Now, each of those terms, most specific, applicable, and method, probably a full talk on their own. In fact, there have been talks on most of these terms at previous JuliaCons. But this is the core semantic that Julia has. This determines precisely what code runs. But it's the only thing that determines what code runs. So you might ask me, well, where are the semantics for things like integers, arithmetic, arrays, strings, memory, floats, pointers, all of the things that make Julia Julia? In other words, how does the system know not just what code runs, but also what code means? And the answer to that is that some parts of the method table are special. There are special entries in the method table that have special semantics. For base Julia, that part of the method table generally has this signature. It's all those method table entries where the first argument is some subtype of core.builtin. Just like in the method table for plus, the first argument was always plus. Now, I have a little bit of a disclaimer at the bottom, since this is a little bit of an oversimplification. But in general, if you have an implementation of dispatch and you have an implementation of each of these built-ins, you have a correct but slow implementation of Julia that will be able to run all of Julia base, all of the packages that don't do anything too crazy. But basically, anything that you think of Julia code, you would be able to run just with an implementation of dispatch and an implementation of all the built-ins that match the signature. Now, I was very careful to say that these are the parts of the method table that define the semantics of Julia base. Because part of what I've been doing a lot over the past 5 or 6 years is explore what would Julia look like as a system if the intrinsics were something other than core.builtin. So if you'll remember the XLA talk I gave at JuliaCon 2019, basically what we did there was we said, OK, rather than using LLVM's semantics as the inductive basis for a system, what if we used XLA instead? And rather than using core.builtin as the special part of the method table, what if you used XLA.HLOup? And if you do that, you get something that inherits XLA semantics. So rather than thinking about memory and pointers and integers and floats and that kind of thing, you think of arrays and I/O and spaces where those arrays get allocated. If you were at my talk yesterday, you might have seen a slight variant of this where the DAE compiler package adds additional semantics to a part of the method table corresponding to all calls to a DAE compiler.variable that are called on a float64 argument. So these sorts of games are something that we've been looking a lot into, that we've been refactoring the compiler to allow exploration of more. Now, I've said that if you have a specification of these built-ins and you have dispatch, you have a fully working correct implementation of Julia. So if that is the case, what does the compiler actually do? So why do we have the compiler? And the short answer is the compiler makes things fast. But how does it make things fast? I think the fair thing to say is it makes things fast by doing two things. The first thing is to figure out large chunks of these intrinsics statically from a given entry point. And in fact, it tries to figure out the largest possible such chunk and then give it to some backend optimizer. In Julia base, that would be LLVM, but in XLA.jl, it would be an XLA. In DAE compiler, it's something written in Julia. So that's one thing it does. The other thing it does is that it has models for the behavior of this part of the method table that corresponds to the intrinsics. So what kinds of models of the behavior might it have? Perhaps the most obvious one, and the one that everybody is familiar with, is it has information about the type behavior. So it knows that if you call core.intrinsics.addInt onto integers, you get an int of the same type back. But more recently, it also has more information. It has information about whether the intrinsic throws an error. It has information about whether the intrinsic has a side effect. And it has information about if the intrinsic throws an error, what kind of error does it throw. So part of the job of the compiler is to lift this information that it has built into it about the intrinsics to information about the whole static subgraph that it extracts for the compiler. And there's also some back and forth here. So improved information that is statically lifted to these static subgraphs might actually allow you to discover a larger static subgraph. The obvious example, again, type inference. If you know two things that are integers will always return an int, then you can go from there and use that information that's going to be an int to discover statically the next intrinsics that it's going to call by devirtualizing that dispatch. But that is a general property. OK, so I want to hand it over to Shuhei for a bit of a deep dive into these middle three. Effects, exception types, and lifetime/escape analysis. And then I'll take it back for effect preconditions and some future musings about what we might do.
OK, so I would like to introduce some of the new static analyses that have been recently added. And the first up is effects analysis. Effects analysis is a new static analysis added in 1.8, and it automatically analyzes the effects of a program. And here you can think of the effects as a set of conditions of programs that are useful for optimizations. And the result of the effect analysis can be checked using base.infer effects. And the effects are represented as a collection of what we call effect bits, each representing some condition of an analyzed method, like consistency of return value and the slowness of the method. And due to the time constraint, I won't be able to explain the meaning of each condition in detail. But if you are interested, please refer to base.assume effects for more detail. Here, as a concrete example, let's take a look at the effects of sine function. And those green effect bits indicate that the conditions are met. So we can see that it generally has good effects. And for example, the green plus C indicates return value is consistent, and green T indicates the execution of sine always terminates quickly. On the other hand, the red T indicates that sine can sometimes throw exceptions. So now let's take a look at what kind of optimizations are possible using these effects. And there are two important optimizations that are what we call concrete evaluation and dead code elimination. And the concrete evaluation evaluates consistent, effect-free, and terminating method calls at compile time, which significantly improves the accuracy of type inference. And dead code elimination is an optimization that removes method calls that are effect-free and not no-throw and terminates if their return values are not used anywhere. There is also something called finalizer inlining, but this is a rather niche feature, so I will skip the explanation here. So let's see how they work in reality. And as a concrete example, let's consider this function effect demo and its call site where the value of the argument x is known to be constant 1.0 and the type of the argument y is known to be float 64. And we can use Kutru package to check how concrete evaluation works. And when we pass the call site to Kutru's descent function, it provides a view like this. And here, the display %3 equal concrete eval indicates that the call to the sign function has been concretely evaluated. And in other words, the compiler confirms from the effect of sign that it is safe to call the sign function at compile time and actually evaluates it to get its return value as constant. Next, let's check dead code elimination. And the optimized area of this function becomes this simple. And with a closer look, you can see that the call to exponential y is completely gone. And this is because if else is just a function call, so with Julia's Jaeger evaluation semantics, its argument exponential y would be executed without optimization. But the compiler knows that x is not infinity, and so the target element is unnecessary in this situation at this call site. And from the effect of exponential y, compiler knows that it can be safely eliminated. And as a result, the call to exponential does not occur at runtime, so saving unnecessary runtime cost. Now I will briefly explain the algorithm of the effect analysis. It's a simple algorithm that is performed simultaneously with type inference and analyzing the effect of each statement and merging them into a single state that represents the effect of the method. And given this effects algo function, we can use Kutru again to observe how the effect analysis works. And when you pass the with effect keyword to Kutru's descent function, we can see how local effects of each statement compose the global method effect. Here, the effects are effect to the right of the top line invoke #16 represents the overall effect of the function. And for example, we can see that the call to sine and cosine to taints no-throw-ness of the method effect, and the set index taints effect freeness of the method effect. So in summary, effect analysis is an analysis integrated with type inference that manages a single state. And as a result, it is very cheap and fast, and it benefits from the inter-procedural information propagation and the convergence guarantees provided by type inference. But because it only manages a single state, it is not data flow sensitive, which means it may not always be accurate. So for example, this effect limit function is actually effect-free, but allocated object XX is not returned and not escaped to anywhere. So the effect of set index on XX does not need to taint the overall method effects, but the current effect analysis doesn't understand data flow of the variable XX, so it ends up tainting the method effect. In other words, to improve the effect analysis in such situations, we need a new analysis that analyzes how variables are used. And this is where the new escape analysis comes in. So escape analysis is a new static analysis enabled from 1.11 that analyzes how objects are used. And for example, it checks whether an object is returned or whether it escapes to the global namespace or it is thrown as an exception. And the result of the analysis can be checked using the eautos.jl script that's located in Julia's test folder. And when you pass effect limit function to code escape function, which is an entry point of the analysis, you can get a view like this. And the green check mark to the left of the statement %1 equal invoke %new indicates that the variable XX doesn't escape to anywhere. Using this analysis from 1.11 onwards, effects are refined in this sort of situations, and as a result, it is now possible to successfully prove the effectfulness of this function, as indicated by the green E mark. Now I explain the design of EA quickly. Unlike the effect analysis, which is performed along with the type inference, escape analysis is performed as an independent analysis on the code representation after optimization. So from 1.11, a new analysis phase has been added to Julia's Julia level compilation pipeline, which we call post-optimization analysis. So EA is implemented as a post-opt analysis, but it's still uncertain, honestly, whether this design will remain the same in the future. The reason is that the analysis on post-optimization IR, especially IR after inlining, can easily achieve a certain accuracy, but it also leads to redundant analysis, and the analysis tends to slow due to the larger IR. And additionally, we also want to differentiate it from the existing LLVM level escape analysis, and I believe it should particularly focus on Julia level 1, especially should focus on inter-procedural information propagation, which cannot be handled by LLVM level escape analysis. So there have been many points for reflection, and EA is still in development stage, but EA has great potential, and with various future applications such as improving memory efficiency and enhancing the accuracy of type inference. So we will definitely keep working on this aspect in the future. Now let's move on to our very latest static analysis, which is exception type inference. From 1.11, the types of exception objects can also be inferred, and it can improve type stability within catch blocks. So consider a function like this with a try-catch block. Until 1.10, the type of the exception object was not analyzed at all, so it was always any. But from 1.11, the type of the exception object is inferred, so the type of error variable here is inferred to be a union of domain error and float 64. I will quickly explain how exception type inference works. And Julia compiler now analyzes all exceptions that may occur within a try block and merge them and propagate it as the type of the exception object of a catch block. Here, the compiler understands the sign x function call may throw domain error, and the throw x definitely throws a float 64 object. Merge those two types and propagates the resulting union as a type of error variable within the catch block. So what this means is that the domain of type inference has expanded to track exception types in addition to return types. And in summary, as you can see in this diagram, the scope of static analysis performed at Julia level compilation pipeline significantly expanded since 1.8 with those newly added static analysis. So that's all from me, and I will hand over my mic to Keno.
All right. One additional thing that the compiler now does, which didn't really fit into any section, so I just put it here, is that we have something called optimized generics. So I said before that we have parts of the method table that have magic properties because they have magic semantics. Now we have more parts of the method table that have magic properties. But rather than having magic semantics implemented not in Julia, these are ordinary Julia functions that have magic semantics for the optimizer. So currently, we have exactly one of these, which is used inside the implementation of scope value. The implementation that we have is called key value. And basically, what it asserts is that if you implement a generic function that is a method of core.optimizeGenerics.keyValue.get or set, which is deliberately a mouthful, then those get and set methods have to obey the lens laws. So if you put something into the collection and then take it out again, those have to be egal objects. And if you don't do that, that's undefined behavior, and you get crashes, and people will write angry blog posts on the internet accusing you of not caring about correctness. So use this very carefully, or don't use it at all. And if you do use it, tell people not to yell at me. OK, let's move on. So all of those features are implemented in Julia 1.10, 1.11, or 1.12. The features I'm about to talk about are either implemented only in PRs or only in my imagination, but I thought it would be fun to talk about them anyway. So if you're watching this anytime after today, the design has probably changed. OK, so the first one of these that I want to do is called effect preconditions, and it starts with this kind of question: is this add inbounds required for performance? And I would do this interactively, but we're running out of time, so I will tell you that I want the answer to be no. I tried this last night, and it regressed. We have some sort of bug where it is actually required on current master, but just pretend the answer is no. And why is the answer supposed to be no? Well, because we know, or LLVM knows, because it's in the same function, that I is always between 1 and length. That's the exact same check that the bounce check does when accessing the array. And LLVM can, in most cases, determine that and just get rid of the bounce check on its own. And that's actually a very good thing, because with all of our fancy analysis that we have now, add inbounds is not only a problem for crashing and undefined behavior if you use it incorrectly, but it can actually also make your code slower even when used correctly, because it makes the kind of constant folding and the kinds of effect analysis that we do more conservative, because there's now this kind of thing that was not proven to always be true, but true only conditional upon the long list of conditions that make inbounds used correctly. So we would like to use inbounds less. So why can't we use inbounds less? So in that example, we could just get rid of inbounds, but there's cases when we can't get rid of inbounds. For example, this one, which is semantically equivalent, but has a function boundary in the middle. And we use LLVM only within one function. We don't use LLVM inter-procedurally. And even if we did, this is a toy example, so maybe it could figure out this one. But in practice, you don't want to have to inline everything into one function just for LLVM to be able to do things like bounce check elimination. So I have an idea of how to fix this. And the idea is to extend effect analysis to not only be able to tell you, yes, this function doesn't throw any errors, or no, I don't know if this function throws any errors, to also be able to say, I know this function does not throw any errors if this predicate is true. So for example, for the add one no throw, it might lift that to a predicate that says, I know this function does not throw any errors if I is between 1 and length a. And then it might inline that into the predicate for foo. And then you run the ordinary optimizer on something that's much smaller. And you get the answer, oh, actually, foo is always no throw. And then you can use that, as usual, to automatically remove the bounce checks, as LLVM would do if it was within the same function. Now, you're not always going to be able to constant fold it to true, but even if it still folds to some simple predicate, like I has to be greater than 10, you might be able to evaluate that predicate, because it's a pure function. You might be able to evaluate that predicate quite eagerly and have very high level in the stack a branch where if that predicate is true, it goes the super fast, no bounce check version. And if that predicate is false, either because you know it's going to throw or because you weren't able to analyze it, it just does what it does right now. This is the infrastructure for this is implemented in this PR. What's not implemented is the automatic lifting of the predicates. But this is something that I'm hoping to do over the next year or so, to hopefully get rid of as many inbounds annotations as possible, and make sure that we retain the same performance without all of the both performance and correctness traps of using add inbounds. OK, another thing that I'd like to do is motivated by this example. So people ask me, now that we have these fancy effect analysis, I have some type that constrains what the value is by assertions in the constructor. So for example, the struct not 0 enforces that the value x inside of it is never 0. So people complain to me, why can't the compiler figure out that if I take x out of this and divide by it, that will never throw a divide by 0 exception? I mean, shouldn't it know that? It knows that it's not 0. And then people say, well, OK, you guys just haven't done a good enough job of building the compiler, so I'll just put assume effects on it and do no throw. But that is actually not legal and will cause undefined behavior. And why is it not legal? It is not legal because constraints in a constructor are not semantically mandatory. Both the compiler and the user have ways to invent values. So how might the user invent values? The user might invent values using reinterpret. The user might invent values using a pointer load. Or the user might invent values using an explicit expr new. And this is deliberate because structs are supposed to have C interoperability. So you're supposed to get them from things other than constructors. But now that we have all of this fancy optimization, maybe it would be nice to say, actually, I don't care about C interoperability, but I really do care that these constraints are mandatory so that the compiler can use them, that I can rely on them for assume effects. So maybe we should have some way to say, actually, this is a constraint type, and the constructor constraints are mandatory. OK, and this is my last slide. And I apologize for cutting into the Q&A time, but I'm happy to stick around. So this is a package I have called interface specs. And to me, this is kind of the final boss of this sort of way of thinking. I haven't done much work on it because the model for the intrinsics that we have in core.compiler is not precise enough to really fully leverage this. But just to give a brief hint of what I might talk about at JuliaCon in 2 years or 3 years, or whenever I manage to make the compiler good enough to actually enable this, interface specs adds 2 intrinsics to the method table, exists and for all. There's various things that you can use them for. You can use them to prove correctness of these sorts of assume effects annotations and optimized generics annotations, and all of these annotations that, if you use them wrong, cause trouble. It would be nice to have some way to at least specify what it means for them to be correct, and interface specs is designed to do them. But more fun thing you can do with them is to use them for testing and to use them for synthesis. So in this example, which works right now, and this is the only example that works right now, I define a function interesting int, which constrains some int, and then I ask it, does there exist an int that satisfies these properties? And if so, give me one. And it's able to find one, and it's able to find one by compiling that expression down to Z3. Just as xla.jl compiled things down to xla, and then asking for an instance that satisfies these constraints. So a little bit of a preview for many years from now. All right. We're happy to take questions.
Questions, anyone? Over there.
So does this mean that we can use the special version of compiler intrinsics whose built-in is in Julia to make all of our math faster? And make it so the compiler knows that x to the 1/2 is the same thing as square root of x?
Maybe. I mean, that's sort of an ill-defined question, right? The question that you want to ask is, what optimizations do you want to permit? And if the question is, can you use this to permit to do rewrite rules, to rewrite x to the 1/2 to square root by some user-defined rewrite rule? The answer is not quite. People have thought about this, and certainly cleaning up the compiler intrinsics and cleaning up what it means to be an intrinsic will help build extension points for doing rewrite systems. But none of what we talked about helps you in building a rewrite system.
Thank you.
We can have another question.
Yes. Where? No. Oh, OK, I don't need to throw it.
Is the optimized generics public? Can I use them in a package?
It's experimental.
Experimental, love that. That means I can use it in base. Should it be used for like array and dict?
Probably not, because array and dict are mutable, and people can do various nasty things to array and dict. And in fact, the package ecosystem does various nasty things to array and dict. And like, it's very, very bad if those interfaces don't implement their contracts. And in particular, the contract of this is not defined with respect to concurrent mutation. In fact, it's not defined with mutation at all. Currently, it assumes that your collection is immutable because it's defined in terms of egality on both the collection and the return value. So if you have an immutable vector, you might want to use it. But basically only if you actually need it for performance, which scope values do, but maybe most other use cases don't. The only reason, like, I'm not saying it wouldn't work. I'm just discouraging it because the consequences of getting it wrong are bad.
Thank you.
All right. In the interest of time, we have to cut it here. But Keno and Shuhei will be around, so you can ask them more questions. Let's thank them again.
Thank you, everyone.